Hello and welcome all to our talk today entitled Exploring the Advantages of Cloud-Native, Easily Consumable, Scalable Formats for Downstream Scientific Exploitation of Point Cloud Data. My name is Trevor Skaggs and I was the primary investigator on the work being performed in this talk. First, I'd like to give you a brief overview about the project itself. So the project objective was to perform a proof of concept, i.e. small-scale transformation of ISAT2 ATL06 product into a cloud-native, easily usable, and scalable format for downstream scientific exploitation. For those of you not familiar necessarily with the ISAT2 and ATL06 product, this is a satellite system that has been put up by NASA that primarily is responsible for gathering snow and ice data around the poles. The ATL06 product specifically is effectively an ice height product generated by NASA that is intended for scientific processing downstream to allow people to look for differences in ice shelf thickness over time. This work is being performed under the NASA Access Grant Program that works towards increasing the scalability and accessibility of all large NASA satellite datasets. So who are we? We are an organization, a company called Element 84. Our primary aim is to help organizations and government agencies, for example, NASA, USGS, etc., solve problems using big remote sensing, life sciences, and transportation datasets. As I mentioned before, my name is Trevor Skaggs. I'm a senior geospatial engineer at Element 84. On this project, I also had assistance from Matthew Hansen, who is a senior software engineer, as well as Dan Pallone, who is the CEO and CTO of Element 84. So in the previous slides, I talked about the project itself, and for those not necessarily familiar with what a point cloud is, I wanted to give a quick overview. So a point cloud are a collection of points that represent a 3D shape or feature. Each point has its own set of X, Y, and Z coordinates, and in some cases additional attributes, as well as timestamps and a variety of other things that could be attached to a given point, which gives you a little bit of ability to do filtering and manipulation of those data sets. Point clouds are most often created by methods used in photogrammetry or remote sensing. In this case, we were looking at obviously a data set that was generated from remote sensing. And as I mentioned here in this slide, remote sensing is a way of collecting data of the Earth by use of satellites or aircrafts. And again, in this example, satellites. On the bottom right-hand side, you can see a visual representation of what a point cloud may look like. It's kind of a cloud of points, just as the name implies. Now, next, I'd like to talk about what entwine point tiles is, which is the file format that we decided to investigate as part of this process. It's a simple and flexible octtree-based storage format for point cloud data. It's encoding agnostic, which is technical jargon, meaning that it has quite a bit of flexibility built into what can go into and out of the octtree-based storage system itself. It has a flexible attribute schema. As we mentioned on the point cloud slide previously, you do have a variety of attributes that can be attached to each point, and having a flexible attribute schema allows us to carry through the ones that we find important. And from a scientific standpoint, being lossless, meaning that all of the data is actually retained in the scheme, is really important. In a lot of cases, you have other organizational systems that will actually filter out some of the points to save some space and therefore make them more quickly accessible. In this format, EPT, they've decided as a group to instead focus on ensuring all the points are retained, but focus on the aspect around how access is done to the points themselves to speed up that performance. There's a couple of groups that support this project directly. So we have entwine.io is the project itself, and that's supported by Hobu Incorporated, which is an open source software development company. Here's an overview of effectively what we did during this project. So the first thing we did was download the data. Then we sorted the data by cycle. Each cycle represents roughly a 90-day operation of the constellation of satellites. We then converted it to an interim format of LAZ. We then performed the index to EPT and subsequently uploaded to an S3 bucket. The sample space that we decided to do for the small scale test that we were performing here is demonstrated on the right-hand side. On the left, you can see the bounding box and the start and end times. This data goes across 6 of those 90-day cycles that we alluded to previously. This is a little bit deep dive technical jargon, but at the end of the day, this is what we were extracting from the original data set itself. As you can see, we're kind of doing those mappings to those X, Ys, and Zs that we talked about in what a point cloud is. I've also included GPS time, which is again an important aspect if you're trying to figure out the differences between data sets over time. And then at the bottom, this is basically that flexible attribute schema that we discussed earlier, and this is attributes that were identified by the scientific community as valuable to them, and most of these are quality metrics. We can kind of scale up and scale down what we carry across, but these are the ones that they've chosen for this initial test. Next, just to give you an overview of what some of the data storage efficiencies look like in this schema, if we were to take the raw HDF5 files, and again, that's how this product is originally delivered by NASA. For the sample tile set we had originally 1,208 files, and that was 88 gigabytes. Once we did the conversion to LAS, we ended up down at about 4.5 gigabytes. EPT generates quite a few more files, which is part of how they organize the data for quick access. And because of that organizational, there's a little bit additional overhead on each file, which makes the file size a little bit bigger than the native LAS. So in this case, we ended up with about 6.4 gigabytes. Quick math here at the bottom, that means we're storing about 7.25% of the original storage size, which also will contribute to faster and more nimble access of the data. Right here is basically that last step that we discussed during the workflow, which is uploading it to an S3 bucket. The point being here is that there's no actual server architecture for serving out the data in this format. Effectively, you can drop it in this S3 bucket, and now if you have something that can consume an EPT endpoint, you are able to just pass it this URL and it just starts chunking through the data and reading what you need. After we had that all set up, we actually had split it up into 6 cycles. These are some visualizations of that data, and so you can kind of see how that progresses across the different cycles and just gives you a good idea of how the data is represented. So on the left-hand side here, we have cycle 1 only, and this is colorized by elevation. You can see there's quite a few holes and maybe some extra slices that were missing, and this is kind of how the program was developed. The intention was that over time they would paint a more and more complete picture by minor adjustments of the satellite as it goes through different cycles. They also had some identified issues in the first cycle that were rectified later on so that the spacing between the lines was much more consistent. On the right-hand side, I've actually turned on all of the data set, and you can actually see those holes fill up quite nicely, and now you have a very good picture of what that ice shelf really looks like, at least across the 1.5 years or so that this data was collected. Next here, I have a couple of slides representing how the data is actually organized, and this is more of a technical deep dive into how exactly those points are being put into different buckets. So on the left-hand side, you can actually see we're retaining the original file source ID and colorizing them by that. That allows us to go backwards in time, and if we identify problem areas in EPT, in the EPT endpoint, we can actually go back to the original source file and maybe rectify that with NASA and say, hey, looks like these ones are a little bit weird. Here's the file ID. Let's see how we can dive into that. On the right-hand side, you're just kind of seeing how the access mechanism of EPT works itself. Red and green are different levels of complexity or scale, and so you can see it's kind of sending and receiving the ones as they actually need them. Next slide here, you can see we can do a little bit more bifurcation even at the cycle level. So on the left-hand side, we have cycle 1 only. It's again colorized by elevation, but we filtered down to a single beam. And on these satellites, each pass actually has 6 beams and sensors that it's using. And so in this case, you can actually kind of filter down to a specific beam, which creates one single track for you to do some scientific calculations against. On the right-hand side, I actually kind of show you these beam pairs. As I mentioned, there's actually 6 total beams, but effectively they're really 3 beam pairs that parallel each other with a 20-meter spacing in between. And this is really nice for identifying smaller scale changes across that landscape. As you can kind of see from the crosshatch, the top one on the right-hand side, you can see that elevation profile. As I turn it on its edge, you can see that 20 meters in between, and that will identify very small changes on the 20-meter scale, which is pretty fine for being a remote sensing data set out at the polar locations. Concludes our talk this afternoon. Going forward, there is still quite a bit of work that can be done in this area to have some additional efficiencies and maybe some additional scalability questions around implementation. But from a small scale perspective, we feel like there was a lot of lessons learned and that we ended up with a pretty good solution that allows for quicker, more easily accessible, and faster integration of these data sets. If you go into the slide deck, you'll actually be able to find links that will take you to the visualization tools. If you navigate to those, the endpoints have been made public for at least a short term so that people can play with the results of what we've done here. I want to again thank you all for your attention, and I will see you at the question and answer session. Thank you.